Hi, this video we will continue looking into compatibility equation. Last time we have encountered a static indeterminate problem when you have a bar stacking between two walls, and then we use the axial deformation to help us to figure out, come up with a second equation. Then we can therefore solve those two unknowns. But I want you to think about this now. The compatibility equation doesn't have to be just like what we had seen for the first example. It can be in various format. So that's the purpose of this video. I want to show you compatibility. It can be different for every single problem, and you want to be flexible for that. So now let's take a look at this one. You have a A36 steel bar showing at here. And it said it's a rigid member. Remember, if it's rigid, it's not gonna warp. It's not gonna become curved member. It's gonna be just always gonna be straight line. Okay. There's a force 15 kilonewton applied downward, and they want us to figure out what's the force at those bar A, B, C, D, and E, F. And we also know there's a AB and EF has cross-section area 25, and CD it's getting skinnier, it's 15 millimeters square. So how do we find those three unknowns, FA and FC and FE? So first, if you isolate this A36 steel bar, look at the FBD, we have those four forces, and ignore this picture right now. Now we have this FBD, and we're about to write down our equations. So force theta y, we have all those three forces, add up minus 15 equal to 0. Then we have our moment equation. If we were to do moment about C, now let's look at it. We have FA times moment of arm will be 0.4, and rotating about C, that's clockwise, so negative. Then FC goes through, that does not show up in the equation. However, we have this external 15 times 0.2, and it's counterclockwise positive. And we have FE, moment of arm will be 0.4, since it's rotating about C, and that's counter, so it's positive. Okay, we have those two equations. Then we don't have any more for static equation. And you say, okay, I could do another moment about A or moment about B, moment about E. Yes, go ahead and try that. If you try that, end up it's actually some variation, something you can derive from those two equations. So in bare bone, you only have two equations. However, we have three unknowns. That's again static indeterminate. Then we need to come up with a third equation. How do we do that? That compatibility equation, it's not going to be like what we had last time when the bar stacking between the two walls. What would be compatibility equation for this particular case? So then we're going to come back to look at this. So imagine those three bars, they're all going to be elongated, right? I mean, something 15 kilonewton pulling it down, all three of them going to be elongated. So imagine the A is being elongated the most, so A to A prime is the longest compared to C prime and EE prime. And remember, AE, this A36 steel bar, is a rigid member, so it's going to be straight, it's going to be linear. So if we made assumption A is being elongated the most, so we're going to get this paragraph here. We're going to get this sketch right here. Then in that situation, kind of going back to the one video we had earlier, we're going to use proportionality or similar triangle to figure this out. And this is going to be how much E prime, that's called delta E. That's the deformation happen in this bar EF. And we also have CC prime. That's going to be deformation happen to the middle bar, which is our CD, I believe. Yes, CD bar. And this, the next one, that will be this one, A prime, and that's going to be deformation in AB bar. Okay, now let's look at this shape. We're going to come up with our equation. Let's see, delta A minus delta E, that's going to be this length right here, over 0.8. This is going to be entire, the big triangle length, 0.8. That's going to be equal to our this length, which is delta C minus delta E for this length right here. Oh, I can totally draw. I forgot. No, I cannot. Okay, so it's going to be this length over this 0.4. Okay, so knowing that, you're going to get the expression of those three deformation. And then we put the deformation equation, which is PL over AE. For delta C, the PL, the P, is going to be internal force at CD bar. That's going to be your FC. FC times L, they have the same length, right? They all have the same length, 0.5. Okay, PL over AE. A has a cross section, AB bar is 15, and the E is made of steel. Now put it back into this equation. Half P for A is going to be internal force is FA, L, AE, and A is 25. Okay, then for solving delta E, we're going to use internal force FE. Then you do the same thing, you added it in and you simplify it. You got your equation. That's your compatibility equation. That is going to become our third equation. Combine with the previous two equations you have over here, then you can solve those three unknowns. So this is another good example to show how compatibility equation can come out to help us solving problem for static indeterminate. And this time, the compatibility equation is based on this geometry and also axial deformation. All right, so hopefully you have a good understanding of this, and I'll see you at the next one. Bye now.